Hi guys, in this video series I will talk about the dynamic programming algorithms and focus on how to code them effectively in Python. Dynamic programming is commonly used in both mathematical optimization and computer programming. It's basically a way to solve problems recursively. To start with a basic algorithm, in this video I will focus on the Fibonacci sequence and how to compute its members in Python. My aim is to show how to write its code effectively so that computing a sequence member will take less time and require less memory. If you are comfortable with the basics of Python, this video will help you to understand how to approach recursive algorithms. For those of you who are not familiar with this special sequence, let me briefly explain it. Each member of the Fibonacci sequence is the sum of the two preceding ones, starting from 0 and 1. So basically, we can write the recursion as follows, where fn denotes the nth member of this sequence. To show you how we can code the Fibonacci sequence effectively, I will present three different approaches. The first approach is using the definition of the sequence directly. That is, in order to compute nth member, namely fn, we first need to compute fn-1 and fn-2. Similarly, in order to compute fn-1 and fn-2, we first need to compute fn-3. So recursively, at the end, we will need to compute f1 and f0, which are already given to us. To see how we would write this logic in Python, let's take a look at our first function in this video. It's a really basic function in terms of the structure. It returns the input n if n is less than or equal to 1, since f0 is 0 and f1 is 1. Otherwise, it calls the function itself again for n-1 and n-2 to compute fn-1 and fn-2 respectively. Since the function calls itself, it's a recursive approach. To understand whether it's an effective algorithm, let's do some experiments. To do that, I will use a line profiler so that we can see how many times each row of the function is called. Here, I make the experiment on computing the fifth member of the sequence. Let's call our function for n equals 5 using the line profiler. Notice that the function is called 15 times as the number of hits for line 6 is 15. Among those 15 calls, in 8 of them we wanted to compute either f0 or f1, which we can understand this from the number of visits to line 7. Let's now examine how many times we need to call function Fibonacci to compute nth member fn. For f0 and f1, one call is enough. For f2, we need 3 calls. The first one is for the summation of f1 and f0, whereas the two are to obtain f1 and f0. Similarly, to compute f3, we need to call the function 5 times. The first one is for the summation, 3 of them are to compute f2, and 1 of them is to obtain f1. To compute f5 and f6, we will need to call it 15 and 25 times respectively. Running the function by yourself, you can see that a large amount of calls will be needed as n increases. Actually, we can show that the number of calls increases exponentially as n increases, making this algorithm exponential time. The main disadvantage of the exponential time algorithms is that it becomes harder to compute for the larger instances. In our case, it is the larger n values. On the other hand, the good thing about this algorithm is that it does not need any memory as it does not store anything. Most of the time, there is a trade-off between the computation time and the memory. Now, I will show you the second approach to code the Fibonacci sequence. This time, we will store some results to speed up the algorithm. Basically, we will decrease the computation time by increasing the memory usage. Let me briefly go over what exactly we will do. Recall that our aim is to compute fn for a given n. To do that, we first need to compute fn-1 and fn-2. Or it would be enough to compute fn-2 and fn-3 since we can obtain fn-1 with fn-2 and fn-3. In the previous approach, notice that we will need to compute fn-2 twice. If we go one more step further, with the previous approach, we will need to compute fn-3 3 times. Do we really need to compute some sequence members more than once? Actually, we don't. After computing each sequence member at the first place, we can store them. Then, whenever we need to compute them again, we will just get them from the storage. Let's take a look at the second function of this video to see how it would work. In the first line, we define a dictionary which stores fn's that has been already calculated. So, in our function, we will first check whether we can get the corresponding member of the sequence from this dictionary. If so, we will just get it without any computation. If not, we will compute it by using the recursion and then store it in our dictionary. The main difference of this approach with the previous one is that we only use the recursion whenever we need, and we compute each required member of the sequence exactly one and then store it. Again, let's take a look at how many times we need to call this function to compute fifth member of the sequence. Notice that we have already stored f0 and f1. So, to compute f2, we just need to call the function 3 times. One for the summation and the other 2 for getting f0 and f1. Similarly, to compute f3, we need to call the function 5 times. One for the summation, 3 for computing f2, and 1 for retrieving f1. Lastly, let's focus on computing f4. We first need to compute f3 and f2, then we need to sum them up. So, we need 1 call for the summation and 5 calls for computing f3. But notice that we don't need to compute f2 from the beginning, because we already stored it in our dictionary while computing f3. So, 1 call is enough to get f2. Thus, in total, we need 7 calls. So, we can say that solution time is order of n. That is, solution time is somehow a multiple of n. On the other hand, the memory usage is also multiple of n. Comparing the previous algorithm, we improved the solution time in this exchange of the memory usage. Lastly, I will show you the best approach to code Fibonacci sequence. We will basically use a bottom-up approach. That is, to compute fn, instead of first computing fn-1 and fn-2 as in the previous approaches, we will start computing from f0 and f1 and store only the last 2 members of the sequence in an iterative approach. To understand the logic, let's suppose that we are at iteration k-1 and we have already computed fk-1 and fk-2. These 2 members of the sequence are the only ones that we store at this iteration. Then at iteration k, we can compute fk by using fk-1 and fk-2. And then we just store fk and fk-1 to use them at the next iteration k+1. It looks like just storing 2 members seems enough. Let's take a look at the implementation. This time, our function looks more complicated than the previous ones. At first, we check if n is less than or equal to 1. If so, the function just returns 0 or 1 as we did in the first approach. Otherwise, we initialize the first step of the function by assigning iteration to 1, fk-1 to 1, and fk-2 to 0. As the iteration is basically k-1, in the first step, k equals to 2, so that we start with f1 and f0. Then until we reach the nth iteration where we can obtain fn at the end, we update fk in each iteration and we increase the iteration number. Lastly, we update the last 2 sequence members, which we store in each iteration. First, notice that the memory usage is almost 0 as we store only 2 values. Then, let's find out how many iterations we need to compute fn. Since we start with f0 and f1, we just need 1 iteration to compute f2. After computing f2, we now store f1 and f2 so that with 1 more iteration, we can obtain f3. Following similarly, notice that n-1 iterations is enough to compute fn. Thus, this algorithm spans order of n times to compute fn. Let's now summarize the approaches and compare their performance in terms of both computation time and memory usage. In the first approach, we use the definition of Fibonacci sequence directly. It does not require any memory, but the computation time increases exponentially as n increases. In the second approach, we use memorization. Compared to the first approach, we improved the computation time in the exchange of memory usage. Lastly, we use the bottom-up approach. This last approach outperforms the first one in terms of the computation time. Also, it outperforms the second approach in terms of the memory usage. Actually, it is the best we can do in terms of both computation time and memory usage, since the computation time is order of n and memory usage is almost zero. This table in fact shows the importance of writing a code effectively. I hope that this video was helpful. Please leave a comment if you have any question. In the next video of this dynamic programming video series, I will talk about Dijkstra algorithm for the short path problem.